Everyone. Hope you are doing very well today. As you all know that we are going to practice some NEET PYQs that has been there previously in the NEET examinations. So let's begin our today's topic, that is NCRT chapter 5 coordination compounds NEET PYQs. This is disclaimer. So today's learning objective, after studying this lecture, you will be able to solve some NEET PYQs of the chapter coordination compounds. And today we are going to cover the topic which is NEET PYQs. Okay, so some previous year questions. PYQ means previous year questions. Today we are going to cover that has been there in the previous NEET examinations in the previous years. Let's begin with our first question, which is a NEET PYQ, and it is based on, or it is covering the NCRT section 5.4. Question is, match the list 1 with the list 2. So as you can see, we have given this table in the question containing two columns. One is for the list 1, which is complex, and the second column is for the list 2, which is for type of isomerism shown by the complex, exhibiting by the complex, right? So we have given the complex. The first one is cobalt, ammonia, whole 5, NO2, Cl2. Then cobalt, ammonia, whole 5, sulfate, bromide. Then the C complex, CONH3, whole 6, Cr, chromium, cyanide, whole 6. And the last complex D is given as cobalt, H2O, whole 6, Cl3. On the other hand, in the list 2, we have given the type of isomerism. The first is solvate isomerism, second linkage isomerism, third is ionization isomerism, and fourth is coordination isomerism. Choose the correct answer from the options given below. We have given the options. Basically, you have to match the list 1, that is the complex, with the list 2, that is the type of isomerism the complex is exhibiting. Options are A is matching with second, B with fourth, B with third, C with fourth, and D with 1. Or A with first, B with third, C with fourth, D with second. Or A is matching with first, B is matching with fourth, C is matching with third, and D is matching with second. Or A is matching with the second, B is matching with fourth, C is matching with third, and D is matching with first. So you have given these options. You have to select the one which is the correct one, right? So you have given some time. Try to remember the concept we have covered regarding the isomerism, or the different isomerism coordination compound has been shown. So using that, you can clearly solve this question. So you have given some time. Try to solve this, and then we will see the correct answer. Okay, let's see. So for this particular question, the correct answer is our option A, that A is matching with second, B is matching with the third, C is matching with the fourth, and D is matching with the first. Okay, let's see. So let's see the different kind of isomerism that are already given in our list 2. What are these how they occur in a particular compound. So first of all, let's see for the solvent isomerism. It involves different number of solvent molecules. Okay, if you want to identify that whether a coordination compound is exhibiting a solvent isomerism or not, you can clearly count or see at the number of the solvent molecules present in the coordination compound. Okay, so solvent isomerism is shown by the complex where uh, there is involves different number of the solvent molecules, and generally it is water, or you can say mostly it is water molecule. Second type of isomerism that is given is linkage isomerism, in which same ligands are bounding through different atoms. Okay, so there are ligands which are same but they are bounding to different atoms within a coordination entity. So that will show the isomerism. The kind of isomerism is linkage isomerism. Third is our ionization isomerism, in which we have different distributions of ions inside and outside the coordination sphere. Okay, so we have ions, they are distributing differently inside and outside of the coordination sphere. Coordination sphere is referring to that square bracket, right, in which are coordination entities present, or are central metal and ligands are present. Okay, so there is different distributions of ions inside and outside of the coordination sphere. Particularly note here, we are talking about ions in the ionization isomerism. Okay, so when we have different number of or different distributions of ions either inside and outside of the coordination sphere in two coordination compounds, then they both are exhibiting ionization isomerism. Okay, last we have given the coordination isomerism, which is actually the exchange of ligands between the two metal centers. When the two metal centers exchange their ligands with each other, then the isomerism shown by those compounds is going to be coordination isomerism. Okay, so these are the four isomerism or type of isomerism already given in our list 2 in the table. So let's now visualize the complex and the factors on which we can decide that what type of isomerism is going to be shown by a particular complex. The first complex we have given is cobalt ammonia whole 5 NO2 Cl2, right? Here if you see, we have NO2 ligand that can bond through either the nitrogen or the oxygen, right? So in the this complex has cobalt as central metal, ammonia and NO2 as ligand, and Cl2, which is present outside of the square bracket, is actually a counter ion, right? Here if you talk about the NO2, and if you know the NO2 structure, NO2 is a ligand which can bond through either the nitrogen or the oxygen with the central metal atom or ion. Okay, it has this ability, and if you see the structure of the NO2, you can easily understand that NO2 in the NO2, if it is nitrogen is in the center and it is making a double bond, forming a double bond with one oxygen and single bond with another oxygen, and there is this negative charge on that single bonded oxygen with the nitrogen, right? So here the nitrogen will be going to the oxygen will be going to bond with the metal. Okay, and in the other case the nitrogen is going to bond with the central metal atom or ion. So NO2 is a ligand which can bind through either nitrogen or oxygen. So it is exhibiting linkage isomerism, which is already given in our list 2 in the option in the second row, right? That is, second isomerism is given as linkage isomerism. So this will exhibit linkage isomerism. That means a molecule or you can say ligand when can bind through different atoms, that is going to be our linkage isomerism. That is what is happening in the linkage isomerism, right? So here also in this complex we have a ligand which is binding through different atoms to our central metal atom, that is cobalt here. So in the NO2 it can either bind through nitrogen or oxygen, so it is showing, or this complex is exhibiting linkage isomerism. So A is connecting with the second one. Similarly, if we talk about our next complex, that is the B, that is cobalt, ammonia, whole 5, sulfate, bromide, right? Now, if we see, it can also exist as cobalt, ammonia, whole 5, and this bromide will go inside and sulfate will go outside, like exchange of ions will be there, right? Like bromide, which is a counter ion, that will go inside of the coordination sphere, and sulfate, which is a ligand, firstly it will comes outside of the coordination sphere and then act as counter ion. So what is happening? It is actually, this complex is also can also exist as this complex where the exchange of the ions have happened. So that means this complex is showing ionization isomerism, which is present in our third row in the list 2. Okay, that means B complex is related to the third row in, or third isomerism given in our list 2. So B is matching with the third one. Okay, that is ionization isomerism due to the exchange of the ions between the inner and the outer coordination sphere. Now, let's talk about our next complex, that is the C, cobalt, ammonia, whole 6, chromium, cyanide, whole 6. Okay, now here ligands can be exchanged between cobalt and chromium here in these in this complex. So this is basically a combination of two complex. In the first one we have cobalt binding with 6 ammonia ligands, and in the second one chromium is binding with 6 cyanide ligands. Okay, if you observe, we have cobalt, like it is, you can say, the structure of this, the coordination number of this complex will going to be 6, because there are 6 available sites that can be bind like by the ligand to the cobalt, right? Similarly in this, the second complex, that chromium have this 6 sites at which the ligand can bind, right? So here in this like in this complex, ligands can be exchanged between our cobalt and the chromium, the metal ion. So between the metal ion, the ligands can be exchanged. So if you put this cyanide from chromium, like cyanide here is bonding with the chromium, right? If you put this cyanide at the place of ammonia after the bonding with the cobalt, and ammonia at the place of the cyanide after the bonding with the chromium, then it will be like similar. Okay, so basically you can do this. So ligands here in this can exchange between the cobalt and the chromium, due to which it is exhibiting coordination isomerism. Okay, so they're coordinating with each other, these two complexes, by exchanging their ligands with the like to bind with the central metal ion, right? So the type of isomerism it is exhibiting is coordination isomerism, which is present in our fourth choice. Okay, so C is matching with the fourth one. Now the only remaining is D. So let's see that. The D complex is cobalt H2O whole 6 whole 3 Cl3, right? Cobalt H2O whole 6 Cl3. Here it can exist with different number of water molecules. So we have, you can see we have a solvent molecule present in our complex, so which is 6 in number, right? So basically you can write this complex as cobalt H2O whole 5 Cl, then H2O Cl2 also, and you can also write it as cobalt H2O whole 4 Cl2, H2O whole twice Cl. And again, once more, you can exchange this water molecule or solvent molecule with the counter ion. Okay, so this complex can exist with a different number of water molecules, right? You can either put it here as one, as a 6 water molecule, as 5 water molecule, and as 4 water molecules. Okay, so this can exist, this complex can exist with different number of water molecule. And what will happen if you decrease the number of the solvent or the water molecules inside the coordination sphere? Basically, you are bringing this counter ion also inside of the coordination sphere to fulfill the valencies of the cobalt, right, to bind with it. Okay, so the coordination number will always be 6 for this complex, for the cobalt. But you can see that inside the coordination sphere, it can the cobalt can bind to different number of water molecules, either 6, 5 or 4. That does means that this complex will show solvent isomerism. Okay, solvent isomerism, which is present in our first choice. So D is connecting with the first one, or D is matching with the first one, and our correct option will be hence A option. That is, A is connecting with the, that is, A complex is connecting with second, B is matching with third, C is matching with fourth, and D is matching with the first isomerism, or the type of isomerism given in our list 2. So correct answer is option A. Let's move to our next question. Okay, so this is a NEET PYQ, and this is covering the NCERT section 5.5.2. Question is, given below are two statements. So we have given two statements, the statement 1 and statement 2. Statement 1 says both cobalt ammonia whole 6 whole 3 positive and cobalt F6 whole 3 negative complexes are octahedral, but they differ in their magnetic behavior. So statement 1 is saying that these two complexes where the central metal is same, that is cobalt, but ligand is different, ammonia and fluoride. These two complexes are both octahedral, but they are differing in their magnetic behavior, that their magnetic behavior is different. Statement 2 is saying that cobalt ammonia whole 6 whole 3 positive complex, this is a diamagnetic, whereas this another complex of fluoride ligand is a paramagnetic one. In the light of above statements, choose the correct answer from the options given below. What are the options? Options are both the statement 1 and the statement 2 are true. Both the statement 1 and statement 2 are false. Statement 1 is true, but statement 2 is false. Or statement 1 is false, but statement 2 is true. So you have given these 4 options, where you have to tell about that which option is corresponding to the correct answer, which option is the correct one, according to the statement 1 and the statement 2 already given, right? So you have given some time. Try to solve this question, and then we will see the correct answer. Okay, let's see. So for this question, the correct answer is option A, that is, both the statement 1 and the statement 2 are true. So we have given this first complex, that is cobalt ammonia whole 6 whole 3 positive. Let's know about this. Here, ammonia is present as a strong field ligand, which is ammonia is a strong field ligand, right? So in the strong field, the electrons will pair up in the lower energy orbitals, right? So in strong field ligand, in the presence of strong field, electrons will pair up in the lower energy orbitals and it will result in the low spin complex with no unpaired electrons. So they are in this, these all lines are interrelated. Okay, first of all, we are claiming that ammonia is a ligand present in this complex, which is a strong field ligand. Due to the strong field, the electrons will pair up in the lower energy orbitals, because the strong field will increase the space or the energy between the two degenerate orbitals, right? Due to which the electrons cannot be jump into the higher energy level, so it will start to pair up in the lower energy orbitals. Now this cause in the formation of low spin complex with no unpaired electrons. Hence, if there is no unpaired electrons, that means it will be diamagnetic, right? If you talk about our another complex, that is cobalt F6 whole 3 negative, here the F negative is given, which is a weak field ligand. Okay, is F negative because if you know the spectrochemical series, F negative is coming at the very starting of the series, having very decreasing or having very weak field, right? So fluoride is a weak field ligand, and in the weak field the electrons will follow the Hund's rule. That means the pairing will start only when all the orbitals gets filled up with one electron. So it will result into the high spin complex with unpaired electron. And why? Because this, in the weak field, this higher energy space will not be available between the two degenerate orbitals, so the electron can easily fill up into the higher energy orbitals, right, following the Hund's rule. And then pairing will start only when all the available orbitals gets filled up singly, right? So this, due to this, we are going to get a high spin complex with unpaired electrons. And if there are unpaired electrons, you can clearly say that this complex will going to be paramagnetic. Okay, now on the basis of these facts about two complexes, you can match the statement 1 and statement 2. Statement was 1 saying that both the complexes are octahedral, they are differing in their magnetic behavior. So yes, the magnetic behavior is different, and other than that, the coordination number is 6 in the both the complex, right? So it can be octahedral both. The statement 2 is given that this first ammonia ligand complex is diamagnetic. It is also correct, it is a diamagnetic because there is no unpaired electron. Whereas the second complex of fluoride is paramagnetic. This is also correct, this is paramagnetic with unpaired electrons. Now you have to select that whether these two are correct or not. So basically you have to choose the correct correct option. So on the basis of these facts, you have studied about these two given complexes. The correct option is going to be option A, that both the statement 1 and the statement 2 are true one. Okay, because statement 1, which is claiming that both complex have different magnetic behavior, this is correct, and both are octahedral. This is also correct as coordination number is 6 in both the complex. Statement 2 is already is also correct because the first complex is diamagnetic and second complex is obvious paramagnetic. So both the statement 1 and the statement 2 are the true statements. So the correct answer will be option A. Okay, let's move to our next question. Okay, so this is a NEET PYQ and this is covering the NCRT section 5.2. Okay, the question is, given below are two statements. Again, we have a statement question. So we have statement 1 and statement 2. Let's see what statement 1 is saying. It is saying that this complex of cobalt ammonia whole 6 whole 3 positive. So this is a complex which is a homoleptic complex, but whereas this another complex given cobalt ammonia whole 4 Cl2 whole positive is a heteroleptic complex. So this is statement 1. Statement 2 is complex cobalt ammonia whole 6 whole 3 positive has only one kind of ligands, but cobalt ammonia whole 4 Cl2 whole positive has more than one kind of ligands. In the light of above statements, choose the correct answer from the options given below. You have given the options on the basis of which you have to you have given the two statements on the basis of which you have to choose the correct option. Options are: both the statement 1 and the statement second are true, both the statement 1 and the statement second are false, statement 1 is true but statement second is false, or statement 1 is false but statement 2 is true. So you have to select the correct option on the basis of the given statement. So try here using the concept of homoleptic and the heteroleptic complex we have studied. What are these? How you identify those? Okay. So you have given some time. Try to solve this. Try to analyze this question, and then we will see the correct answer. Okay. Let's see. So for this question, the correct answer is option A, that both the statement 1 and the statement 2 are true. Let's see how. So homoleptic complexes, they have only one type of ligands. Homo means same. Wherever you will see the homo, that means it is somewhere referring to same. So homoleptic complexes, that means the complex will have only one type of ligand present in it. Meanwhile, heteroleptic complex, they have more than one type of ligand in it. Okay, the complexes which are having more than one type of ligand or different type of ligands present in it. If you observe the statement 1, which is saying that this cobalt ammonia whole 6,3 positive is a homoleptic complex, so this is true because it has only ammonia as a ligand, right? So this is homoleptic. This complex is homoleptic. Why? Because it has only ammonia ligands, only one type of ligand present in it. Okay, so this another complex, second complex, which is given as cobalt NH3 whole 4 Cl2 whole positive, this is heteroleptic. Why? Because it has two different type of ligands in it. First is ammonia, second is chloride ion. Right? So in this complex, we have two types of ligands. So it is heteroleptic. The first complex given is a homoleptic because it is having only one type of ligand, that is ammonia. That means the statement 1 is already true, right? Because it is considering, or it is saying, that first complex is homoleptic because yes, why not? Because it is only containing one type of ligand. And the second complex, that is cobalt NH3 whole 4 Cl2, is a heteroleptic, and this is also correct because it is containing two types of ligands. Statement 2 is also correct because it is saying that first complex has only one kind of ligand and second complex has more than one kind of ligand. So our correct option is the option A, that both the statement 1 and the statement 2 are true. Right? Okay, let's move to our next question. This is a NEET PYQ and this is covering the NCERT section 5.2. Question is, homoleptic complex from the following complexes is. So you have to choose the homoleptic complex from these given options. Options are potassium trioxalato-aluminate third, diamine chlorido N platinum second, pentaamine carbonato cobalt third chloride, or triamine triaqua chromium third chloride. You have given some time. Try to solve this and then we will see the correct answer. Okay, let's see. So for this given question, the correct answer is option A, that is potassium trioxalate to eliminate third. So homoleptic complex is basically a metal complex where the ligands or all the ligands are identical, are same present in the complex, right? So the first complex given is potassium trioxalate to eliminate third, which you can write the formula of it as K3 aluminium C2O4 whole thrice, right? Potassium trioxalate to eliminate third. It contains only oxalate ligand around the aluminium 3 positive, around the central metal ion, right? That means it is a homoleptic complex. So all three ligands are oxalate. So this is a homoleptic complex. If you talk about the second complex given, which is diamine chlorido nitrito and platinum second, the formula of it will be platinum ammonia whole twice chlorine NO2. Here it is containing different ligands, ammonia, chlorine, NO2, right? Different type of ligands is present in this complex. So this is a heteroleptic complex. If you talk about the third complex given is pentamine carbonato cobalt third chloride. The formula of it will be cobalt ammonia whole 5 CO3Cl, right? So it contains different ligands. First is ammonia and second is CO3, 2 negative. Okay, carbonato you can say. So we have different different ligands present in this complex, right? So here also this complex will be heteroleptic complex due to the presence of different type of ligand in it. Fourth complex given is triamine triaqua chromium third chloride, whose formula you can write it as chromium ammonia whole thrice H2O whole thrice Cl3. Here we have given triamine, so 3 amine, triaqua, so 3 aqua, aqua means water, and chromium, central metal ion having +3 +3 oxidation state, and chloride is present as counter ion. It or this complex is also containing different ligands, first ammonia and then this water molecule. So it is also a heteroleptic complex. So we have to identify the homoleptic complex, which is only one given in our correct option, which is option A. Potassium trioxalate to eliminate, where only one ligand is present, that is oxalate, so it is a homoleptic complex, and this option A is going to be our correct answer. Let's move to our next question. This is a NEET PYQ and this is covering the NCERT section 5.2. Question is, which complex compound is most stable? Options are cobalt NH3 whole 4 H2O bromine NO3 whole twice, cobalt NH3 whole thrice NO3 whole thrice, cobalt Cl2 En whole twice NO3, or cobalt NH3 whole 6 whole twice SO4 whole thrice. You have to select the complex compound that is more stable. So you have given some time, try to solve this and then we will see the correct answer. Okay, let's see. So for this given question, the correct answer is option C, that is the complex cobalt Cl2 En whole twice NO3. Stability of a complex can be determined using chelate effect. Remember the chelate effect we have studied, in which there is a presence of chelate ligand which forms a ring-like structure around the central metal atom after binding to it at different sites with the different donor atoms, right? So, and second factor that is going to determine the stability of complex is nature of the ligands. And this we are going to tell based on the spectrochemical series. Next is charge and the size of metal ion present in our complex. Then the fourth factor is crystal field splitting energy. So the first complex given is cobalt, ammonia, whole 4H2O, bromine, NO3 whole twice, right? So for this, it is containing only monodentate ligands. Monodentate means which are having only one denticity. That means which are having only one donor atom that can be bind to the central metal ion, that is cobalt. So here all the ligands are monodentate and they are mixed ligands. Ammonia, water, bromine, NO3, they all are monodentate ligands. In the B complex, we have given cobalt, ammonia whole thrice, NO3 whole thrice. Here also only monodentate ligands are present, ammonia and NO3, right? Only having one donor atom which can bind to central metal ion, right? So we have to find the most stable one complex, which you can determine using these four factors: whether there is a presence of chelate effect, whether what will be the nature of the ligand, the charge and size of metal ion, and the CFSE. The C complex is cobalt, Cl2, En whole twice, NO3. Now it is containing bidentate ligand, right? Which is En, ethylene 1,2-diamine. This En is a bidentate ligand. That means it is going to have two denticity. That means it is going to have two donor atoms which can bind to the central metal ion, which is actually two nitrogen atoms present in this compound or in this ligand. So here in this complex, chelate effect is present, right? Because this is a bidentate ligand, this can bind through two nitrogen atoms or donor atoms to this cobalt, forming a ring-like structure around the central metal atom and provide the stability to the complex. So this is the chelate effect shown by this ligand. So here in this complex, chelate effect is present. In the D complex, we have cobalt, NH3 whole 6 whole twice, SO4 whole thrice. Here, it is containing all NH3 ligands, right? SO4 is a counter ion present outside of the coordination sphere. But ammonia is a ligand and cobalt is only having all ammonia ligands, which is a strong field ligand. So, it is having symmetric structure due to the presence of same ligand, right? So that means the only most stable complex is going to be the one present in our option C due to the presence of chelate effect. Okay, due to the chelating ligand En, ethylene 1,2-diamine. So the correct answer will be option C, that is cobalt, Cl2, En whole twice, NO3. Let's move to our next question. This is a NEET PYQ and this is covering the NCERT section 5.3.2. Okay, though the question is that IUPAC name of the complex AgH2O whole twice, AgCN whole twice is. So you have given this complex, you have to name it according to the IUPAC. The options are diaqua silver second, diacyanido argentate second, or diacyanido silver first, diaqua argentate first, or diaqua silver first, diacyanido argentate first, or diacyanido silver second, diaqua argentate second. So you have given some time, try to solve this, then we will see the correct answer. Okay, let's see. So for this question, the correct answer is option C, that is dia-aqua silver first, diacyanido argentate first. So, determination of oxidation state of silver in the complex. So, first of all, you have to identify the oxidation state of the silver present in this complex. So, we have two silvers. So, for this first complex, AgH2O whole twice whole positive, the H2 here is a neutral ligand, right? So, what does this do? Because H2 is a neutral ligand, it is not going to contribute to any charge. So the overall charge present on the complex will going to be the oxidation state of the central metal, that is silver. So overall charge of this part is +1. So therefore the silver is in +1 oxidation state in this complex. Now for the second, AgCN whole twice whole negative, cyanide ion has a charge of -1 over it, so it will contribute to the oxidation state. Here overall charge of this part is -1, right? So the Ag will be in +1 oxidation state, because it will become like, you have to identify for the Ag, right? Let's suppose Ag has X. So X -2, because 2 times -1 will be -2. -2 is equals to the overall charge on the complex, that is -1. When -2 go here at the right hand side, it will become +2, and +2 -1 will be +1, right? So silver also here is having +1 oxidation state. Now the naming rules you have to apply. The cation is named first, followed by the anion. So you have to name first the cation part, that is the first complex part. So AgH2O whole twice whole positive. Now you can write it as, first of all, the ligand name with its number. So dia-aqua silver and its oxidation state in the Roman numeral first. Okay, dia-aqua silver first. Then you have to write the anion part, AgCN whole twice whole negative. Here we have, first of all, have to write the ligand name with the number. So diacyanido. Why cyanido? Why we are introducing a O in the end of the name? Because it is an anionic ligand. So diacyanido argentate, because we call silver as argentate, and argentate, 8 is coming at the end of the name because this is an anionic complex. Okay, as per the rules. So this name will of this anionic part will be diacyanido argentate first. First is the oxidation state of silver. So the correct option is going to be our option C, the correct name of the given complex, that is dia-aqua silver first, diacyanido argentate first. Okay, let's move to our next question. So this is a NEET PYQ, and this is covering the NCRT section 5.5.5. The question is, order of the energy absorbed which is responsible for the color of complexes. So we have given these three complex: nickel H2O whole twice En whole twice whole 2 positive. B is nickel H2O whole 4 En whole 2 positive. And C is nickel En whole thrice whole 2 positive. So you have to tell the order of these complexes basis on the energy they are absorbing, which is responsible for their color. The options are: C complex is having the highest energy absorbed, then B, then A. C is having the highest energy absorbed, then A, then B. B is having highest energy absorbed, then A, then C. Or A is having the highest energy absorbed, then the B complex and the C complex. So you have given some time, try to solve this question, and then we will see the correct answer. Let's see. So for this question, the correct answer is option B, that C complex is having the highest energy absorbed, then the A and the B complex. The color of a complex is determined by the energy gap between the splitted d orbitals of the metal, represented by, this gap is represented by delta, right? Now, spectrochemical series will show the order of the ligand field splitting, right? From the weak field ligand to the uh, strong field ligand. Here, we have only two types of ligands present in our complexes, in all the three complexes, water and EN, ethylene 1,2-diamine, right? And if you talk about their their strength or their order of field splitting, H2O will be a weak field ligand than the EN, ethylene diamine. So EN will be strongest or stronger field ligand than the H2, because H2 is a neutral ligand, right? So according to the spectrochemical series, we determine the order between the ligands for their field splitting. Now for the given complexes, this nickel H2O whole twice, En whole twice, whole 2 positive, this complex is having 2 water molecules as a ligand and 2 En molecule as a ligands, right? The second complex, NiH2O whole 4, En whole 2 positive, has 4 water molecules as ligand and 1 En molecule as ligand. And lastly, the En is a higher in the spectrochemical series than water, we just have seen, right? In the spectrochemical series, En is strong field ligand comparative to the water molecule. So our presence of more number of En ligands means that larger crystal field splitting will happen. That means high energy will be going to be absorbed. Okay, so more water molecules or more water ligands means smaller crystal field. That means lower energy will going to be getting absorbed. Okay, this is the direct relationship that we are going to use in this solution. So our third complex, that is nickel En whole thrice whole 2 positive, this is having 3 En ligands and it is going to have highest energy absorption. Okay, and this second complex, nickel H2O whole twice, En whole twice, it is having 2 En and 2 water molecules, right? So they are equal. So this will going to be intermediate. And the first complex, that is a nickel H2O whole 4, En whole 2 positive, this is the B complex, right? Here water molecule are 4, but En molecule as a ligand is only 1 in number comparative. So here the energy absorption will be lowest among the given 3 complexes. So the order you can arrange will be highest for the C complex due to the presence of 3 En molecules, which is going to be responsible for the highest energy absorption due to their greater or due to their larger field splitting than the water molecule. Then comes in the order the A complex, because of the presence of equal number of the water ligands and the En ligands, and then lowest energy absorption will be done by the B complex because of the presence of higher number of water molecules as ligands in it comparative to the En ligand. Okay, so our correct option, therefore the correct option is going to be option B, that is highest for C, then for A, then for B. Highest energy is absorbed by C complex, then for then by A complex, and then by B complex. Yeah. Okay, let's move to our next question. This is a NEET PYQ and covering the NCERT section 5.5.2. So this is given as match list 1 with the list 2, where list 1 is containing different complex compounds, coordination compounds, and list 2 is containing the magnitude of the magnetic moment. So list 1 is having the complexes iron Cn whole 6 whole 3 negative, iron H2O whole 6 whole 3 positive, iron Cn whole 6 whole 4 negative, and iron H2O whole 6 whole 2 positive. Similarly, in the list 2, we have given the value of magnetic moments: 5.92 Bohr magneton, 0 Bohr magneton, 4.90 Bohr magneton, and 1.73 Bohr magneton. You have to choose the correct answer from the options that is given below. The options are: A is matching with fourth, B with the first, C with the second, and D with the third. A is matching with fourth, B with second, C with first, and D with third. A is matching with second, B is matching with fourth, C is matching with third, and D is matching with first. Or A is matching with first, B is matching with third, C is matching with fourth, and D is matching with second. You have given some time, try to solve this using the concept of magnetic moment or calculation that we have studied, and then we can see the correct answer. Okay, let's see. So for this question, the correct answer is option A, that in the list first, A is matching with fourth, B is matching with first, C is matching with second, and D is matching with the third. The magnetic moment, if you understand, this is given by the formula mu is equals to under root n plus 2 Bohr magneton, where n has specific meaning. So n is the representation of number of unpaired electron present in R, like present in the atom, in the central metal, in the complex. Okay. For the first complex, iron Cn whole 6 whole 3 negative. Iron is in +3 oxidation state, so its electronic configuration will be D5. D5 means we have 5 unpaired electron. And here the cyanide ligand is present, which is a strong field ligand. So it will cause the pairing of electrons. So the low spin complex will going to form, and you are going to get n equals to 1 unpaired electron after the pairing happens. So mu will be equals to, you put n equals to 1 in the value in the formula of mu for the calculation, which is under root n plus 2, n will be 1, so 1 plus 2, 2 plus 1 is 3, 3 times 1 is 3, under root 3 means 1.73 Bohr magnet. So the value of the first complex magnetic moment is 1.73 Bohr magneton, which is present in the fourth value of the magnetic moment given in our list 2, right? So A is matching with the fourth one. For the next complex B, FeH2O whole 6 whole 3 positive. Iron here is in +3 oxidation state again, and having the electronic configuration of D5. Okay. D5 means the 5 unpaired electron is going to be present in the d orbital. Now if you talk about the ligand, here is a water molecule which is a weak field ligand. Weak field ligand means no, it will not cause any pairing of electrons. So we will get a high spin complex where we get 5 unpaired electrons. That means the mu will be under root 5, 5 plus 2, 5 plus 2 is 7, 7 times 5 is 35, under root 35 is 5.92 Bohr magnet. Right? Now this is matching with the first choice in the list 2. The B is matching with first. C complex, iron Cn whole 6 whole 4 negative. Here the iron is in +2 oxidation state, and the electronic configuration here for the iron is D6. D6 means 4 number of unpaired electron and 1 paired electrons. So here the cyanide is present, which is a strong field ligand, right? Strong field ligand will cause the pairing of electron. So we will get, due to which we will get low spin complex. That means all the electrons will get paired up. So mu will be equals to 0 because N we got is 0. We get no unpaired electron. So mu will be 0. That means the C complex is matching with the second choice. Lastly, we will see the D complex, that is iron H2O whole 6 whole 2 positive. Here the iron is in plus 2 oxidation state again, and electronic configuration for it will be D6. That means 4 unpaired electron and 1 paired electrons. So here the ligand present is water molecule, which is a weak field ligand, or you can say neutral ligand. So it will not cause any pairing of electrons. That means we will going to get high spin complex. That means 4 unpaired electrons will going to be remain as unpaired. That means N will be 4. When you put it in the value into the formula of magnetic moment, mu will become under root N plus 2. N is 4. 4 times 4 plus 2. 4 plus 2 is 6. 6 times 4 is 24. So under root 24 is equals to 4.90 Bohr magneton. That means the D complex is matching with the third choice, 4.90 Bohr magneton. So the correct option after the after analyzing each complex given in the list first, the correct option is option A. A is matching with the fourth choice, B is matching with the first one, C is matching with the second one, and D is matching with the third one. Right? So option A is going to be our correct answer. Okay. So this is a NEET PYQ and this is covering the NCERT section 5.5.4. Question is, which of the following is correct order of increasing field strength of the ligands to form the coordination compounds? So you have to tell, or you have to select the correct order of the increasing field strength of ligands to form the coordination compounds. Basically, we have given this different orders between the different ligands representing the increasing field strength of ligands. You have to select the correct one. Options are: highest field strength is for C2O4 2 negative oxalate, then cyanide, then fluoride, then SCN negative, or Cn negative having highest, then C2O4 2 negative, then SCN negative, then fluoride ion, or fluoride ion having highest field strength, then SCN negative, then C2O4 2 negative, then Cn negative, or cyanide ion is having highest field strength and then C2O4 2 negative, then F negative, then SCN negative. So let's see. So for this question, the correct answer is option B. That is highest for cyanide negative, then for C2O4 2 negative, then for SCN negative, and then for F negative. So spectrochemical series is the series which arrange the ligands in the order of increasing field strength on the basis of the manner that how much it can strongly split the 2d orbitals into the higher and the lower energy level. General order of some common ligands in the spectrochemical series is as follows. You can see highest is for cyanide, lowest for iodine, bromide, chloride, fluoride, then water, then ammonia, and then comes the strongest, that is cyanide ion. Right? So this is some common ligand spectrochemical series. You have to just identify the ligands that is already given in our options. So fluoride is a weak field ligand. SCN negative, thiocyanate, it is also a weak field ligand, but it is comparatively stronger than F negative. Then comes the oxalate ion, that is also an intermediate field ligand. And then the cyanide ligand will come, which is the strongest field ligand. So our correct option is going to be, or the correct order is going to be present in our option B. That is strongest field ligand will be cyanide ligand, then C2O4 2 negative, then SCN negative, and then F negative. Right? Okay. Okay. Thank you so much. That's all for today's chemistry session. Thank you.